Okay, let's unpack this. You've given us a stack of fascinating material here, diving deep into the world of embodied AI and the rise of general-purpose humanoid robots.
Yeah.
It's a complex space, isn't it? Bridging cutting-edge artificial intelligence, incredibly sophisticated hardware engineering, and some really big fundamental questions about our future.
It absolutely is. And what's happening right now is a truly fundamental shift, I think, in artificial intelligence. We're moving AI out of the abstract digital realm it's largely inhabited.
Right out of the computer screen.
Exactly. And into our physical reality. It's not just thinking anymore. It's doing, in the real world.
Right. And our mission for this deep dive, to cut through the noise, maybe extract the most important insights from the source material we've got, and give you, the listener, a clear, detailed understanding of how these incredible machines work, who's building them, what they can do now, and crucially, where this is all heading.
Yeah, trying to get at the why and the how.
Exactly. Uncover some surprising facts and hopefully give you a few aha moments along the way, all without getting lost in the technical weeds, hopefully.
Think of it as getting the insights you need to understand this revolution, grounded in the reality of the technology and, well, its implications.
Exactly. And to really grasp what's happening, let's start by stepping into a scene that, frankly, still feels a bit like science fiction, but is becoming reality right now.
Okay.
Imagine a factory floor. Maybe it's late at night, the main assembly line's humming along, mostly managed by traditional, bolted down automation.
The usual test.
The usual stuff. But now, among the static machinery, picture a human-sized robot. This isn't just a robotic arm in a cage. It's walking freely, sensing its environment.
Okay, I'm picturing it.
It approaches a complex assembly jig, reaches in, and precisely inserts a sheet metal panel. It does this flawlessly, repeatedly. Now, here's the part that really gets interesting. And nearby, a human technician is watching. And the robot, powered by sophisticated AI, like a vision language model, is actually communicating with them.
Talk to the technician.
Yeah, answering questions about its task progress, its status, maybe even flagging a potential issue it's detected.
And this isn't a scene from a distant future film. Based on demonstrations and industry reports, we're seeing this begin to happen today in places like BMW's manufacturing plants.
Which is just incredible to visualize. So the core question powering this deep dive is, how did we get from abstract code and algorithms that live purely in the digital world to physical machines capable of not just performing complex tasks, but also perceiving, reasoning, and even communicating in our messy, unpredictable physical reality? And what does this profound leap mean for all of us and for what comes next?
Welcome to a deep dive into embodied AI and the dawn of general-purpose humanoid robots. This isn't merely about creating machines that resemble humans. It's a fundamental transformation in artificial intelligence itself, extending its reach from screens and servers squarely into the tangible world we inhabit.
We've got a lot of ground to cover, from the foundational concepts that make this even possible to the intricate hardware that gives these robots their bodies, the complex AI brains that power them,
Right.
the companies leading the charge with real-world deployments, and the big challenges, opportunities, and even the complex ethical questions that come with this territory.
So think of us as your guides as we navigate this incredible landscape of innovation.
Let's do it. Where do we start? Foundational concepts.
Let's begin by defining our terms. What exactly is embodied AI?
Great place to start. At its heart, embodied AI is artificial intelligence that is integrated into a physical system. Think robots, self-driving cars, advanced automated factories, that kind of thing.
Okay.
The defining characteristic is that it perceives its surroundings using sensors, it reasons about what it perceives, it acts upon its environment using actuators, and critically, it learns and adapts through direct physical interaction with the tangible world around it.
That direct interaction, that situatedness in a physical environment, that's the absolute key differentiator, isn't it?
Yeah.
Contrast this with disembodied AI systems like the large language models, LLMs, powering chatbots, or even traditional AI like recommender systems.
Right. Systems like ChatGPT operate purely in abstract digital spaces. They process data from absolutely vast but entirely pre-existing digital libraries. They consume trillions of words of text, code, images, stuff humans put online.
Their knowledge is derived from identifying patterns, relationships, statistical probabilities within that massive digital data set. It's not knowledge gained through lived experience or interacting with physics.
No bumping into things.
No, none of that. It's derived understanding from passive consumption of data. You could say they are thought first, they process information and generate outputs within their digital domain.
Embodied AI, on the other hand, is fundamentally action first. These systems gain intelligence by actively moving, sensing, and acting in the environment. Their understanding and capabilities emerge dynamically from that continuous feedback loop between their actions and the environment's response. They learn by doing, by experiencing the world's physics and dynamics firsthand. Their intelligence is inextricably linked to being situated in a specific environment and interacting with it.
And this entire process revolves around the perception-action loop. This is the fundamental engine driving all embodied intelligence.
Okay, let's break down this loop because understanding it is crucial. It's a continuous cycle, constantly running.
First, the robot engages in perception. It gathers data from its environment through all its senses, its cameras acting as eyes, maybe force sensors feeling weight, joint encoders understanding its body position, microphones hearing sound.
All the input.
All the input, potentially even tactile sensors for touch.
Then comes reasoning and decision-making. The AI processes that deluge of sensory data to build an internal understanding of the situation. It assesses what's happening, compares it to its goals or instructions, and decides on the most appropriate action to take next.
Makes a plan, basically.
Right. After the decision, it's time for action. The robot executes the chosen movement or task using its physical components, its motors, grippers, legs, etc.
It does the thing.
It does the thing. And finally, there's feedback. The action the robot took inevitably changes the environment, even if subtly, or changes the robot's own physical state.
And that change is immediately sensed, providing new input for the next cycle of perception. The loop starts again, with the robot continuously updating its understanding and adjusting its behavior in real time.
So it's constantly learning and adjusting based on what happens.
Exactly. This constant, rapid cycle is what allows embodied systems to learn, adapt, and behave intelligently, particularly in dynamic, unpredictable environments. It's not just a robotic concept, it's how biological systems, including us, interact with the world.
Think about something as simple as reaching for a cup. You perceive the cup's location and your hand's location, perception. Your brain plans the movement, reasoning. Your muscles move your arm, action. As your hand moves closer, your eyes and proprioceptors send back information about your hand's position relative to the cup, allowing you to make tiny, continuous adjustments.
That's the feedback, feeding back into perception and reasoning again, constantly correcting.
Exactly.
And it's important to note that embodiment isn't a simple on-off switch. It exists on a spectrum, really.
How so?
Well, the key element is that interactive learning loop within an environment. While a robot in a factory is clearly physically embodied, an AI agent operating within a highly realistic, physics-based simulation environment.
Like a video game world.
Sort of, but a very accurate one.
Yeah.
That AI can also be considered embodied within that virtual world because it engages in the same perception-action loop and learns from its interactions there.
Ah, okay. Which leads us directly to the concept of sim-to-real transfer, right? A cornerstone of modern robotics development. It's about training AI or robot behaviors in simulation and then successfully transferring those learned skills to a physical robot.
Exactly. Given the challenges of collecting vast amounts of real-world data, and let's face it, the risks of training through trial and error with expensive hardware.
You don't want to break the shiny new robot on day one.
Precisely. Simulation is indispensable. Platforms offering physically accurate virtual environments are crucial proving grounds.
So what are the big advantages of using simulation?
Well, first, data generation at scale. You can create massive, diverse synthetic data sets, including scenarios that are rare or dangerous to recreate in the real world.
Like an emergency stop situation.
Exactly, or handling very unusual objects. Industry data shows you can generate hundreds of thousands of realistic trajectories in hours, equivalent to thousands of human hours of effort in the real world. This is vital for data-hungry deep learning models.
Okay, massive data. What else?
It offers safety and cost-effectiveness. Training in simulation is a safe sandbox. Robots can learn through reinforcement learning, making mistakes, and failing repeatedly.
Without consequence.
Right. Without damaging themselves or their surroundings. It's vastly cheaper than physical trial and error.
Makes sense.
There's also unparalleled control and repeatability. You have precise control over every aspect of the environment: lighting, object properties, physics parameters. This is essential for systematic testing, debugging algorithms, and ensuring consistent training conditions.
And it must speed things up.
Dramatically. It accelerates development. Simulations can run much faster than real-time, and you can run many simulations in parallel. This allows for rapid iteration on AI models and control policies.
Okay, simulation sounds great, but it's not the real world. How do you deal with the differences, the reality gap?
That's the big challenge with Sim2Real, bridging that gap. Techniques like domain randomization are key here.
Domain randomization, what's that?
It means deliberately varying parameters within the simulation, textures, lighting, object positions, even physics parameters like friction. By doing this, you force the AI model to learn policies that are robust enough to handle the variations it will inevitably encounter in the real world. It learns not to rely on one specific setup.
So you make the simulation messy on purpose so the AI is ready for a messy reality.
Kinda, yeah. High-fidelity physics engines in simulators also help, aiming to make the virtual world as close to reality as possible. And sometimes, training higher-level AI policies that are less sensitive to low-level physics inaccuracies can improve transfer.
Interesting.
What's truly fascinating now is the emerging symbiotic relationship between AI and simulation itself. AI is starting to build better simulators.
Wait, AI is creating the simulations now?
Some research is heading that way. Generative AI and what are called world foundation models are being explored to automatically generate realistic, diverse training scenarios, and even predict how the environment will change based on potential actions, creating more dynamic and useful simulations.
Wow. So AI helps build better sims, which helps build better AI. A feedback loop.
Exactly. This feedback loop is powerful. AI helps create more sophisticated simulations, which in turn accelerates the development of even more capable AI. It's essential for tackling the complexity of the real world and improving sim-to-real transfer.
Okay, foundational concepts, the perception action loop, the critical role of simulation. That sets the stage really well. Now let's shift focus to the physical side. The robot itself. What exactly makes up the body of a general-purpose humanoid robot?
Right, the physical form is incredibly important. It's the interface to the real world. And it's a complex integration of components. The actuators that act as muscles, the sensors providing senses, the hands enabling manipulation, and the power and compute systems sustaining it all.
Let's start with the muscles, the actuators. These convert energy into motion, right?
Precisely. The primary types used in modern humanoids are electric and hydraulic.
Okay, electric versus hydraulic. What's the difference?
Well, electric actuators are really the trend now. They're clean, quiet, generally more energy efficient, and offer extremely precise control over speed and position.
But maybe not as strong.
Historically, yes, less powerful than hydraulics for high-torque applications, but their capabilities are rapidly improving. Techniques like quasi-direct drive, or QDD, which use powerful motors with minimal gearing, are enhancing performance, especially something called back-drivability.
Back-drivability.
It means you can move the robot's joints passively, like if you push on its arm, it moves smoothly rather than being rigidly locked. That's useful for safety and certain kinds of interaction.
Okay. And hydraulics.
Hydraulic actuators provide superior power and strength, often with good speed. Think of Boston Dynamics' early hydraulic atlas. Remember those videos? Raw power, dynamic movements.
Oh, yeah, the backflips.
Exactly. But they are less precise, more complex systems, can have issues with leaks, messy, and noise, and generally require more maintenance.
So the choice depends on what you need that joint to do, like power for legs, precision for fingers.
Exactly. High torque for legs and hips, maybe high precision for fingers. But it's interesting, Boston Dynamics' recent move to an all-electric Atlas shows that electric actuators are now meeting the demands, even for highly dynamic, powerful robots. That's a big shift.
Is there anything holding back mass production here?
Yeah, a potential bottleneck, particularly for scaling mass production of these electric humanoids, seems to be the supply chain for certain high-precision components. Things like planetary roller screws.
Planetary roller screws.
They're crucial for translating rotary motion from a motor into linear force very efficiently and precisely. They are expensive and complex to manufacture, and the capacity to make enough of them might be a constraint if you want to build millions of robots.
Okay, something to watch. Let's move on to the robot's senses. The sensors, its interface to the world.
Right, gathering all the data necessary for perception, navigation, interaction.
So vision first, cameras.
Vision is paramount. Humanoids use various cameras. Standard RGB cameras for color and texture, depth cameras to measure distance, and stereo cameras, pairs of cameras, for 3D perception and navigation, like how our eyes work.
How many cameras are we talking?
It varies. Robots like Figaro 2 reportedly have multiple cameras, maybe 6 in their head unit alone. Tesla's Optimus also uses a camera-centric vision system, leveraging their experience with the FSD computer from their cars.
What about other vision sensors, like LiDAR?
LiDAR is also common. It uses lasers to create highly accurate 3D maps of the surroundings. It's essential for precise navigation and obstacle avoidance, especially in tricky visual conditions where cameras might struggle.
Okay, so eyes and mapping. What about sensing its own body?
That's proprioception, the robot's sense of its own body state. This involves things like joint encoders.
Measuring the angle of the joints.
Exactly, angle and speed. Then you have force torque sensors, often placed at joints or in the hands or feet. These measure the forces being applied or experienced, which is critical for things like maintaining balance while walking or controlling how hard you grasp an object.
Makes sense. You don't want to crush the thing you're picking up.
Precisely. And then there are IMUs, inertial measurement units.
Like in your phone?
Similar tech, yeah. They contain accelerometers and gyroscopes to sense linear acceleration and angular velocity. This gives the robot data for balance, orientation, and stable movement.
Okay. Vision, mapping, body sense. What about touch?
A rapidly developing and really crucial area is tactile sensing, giving the robot a sense of touch. The goal is to replicate human touch capabilities, sensing contact, pressure, texture, even detecting if something is slipping in its grasp.
That sounds incredibly difficult.
It is, but it's vital for delicate manipulation and especially for safe physical interaction with objects and humans.
How are they doing it?
There are innovations like eSkin flexible sensor arrays that can cover robot surfaces, particularly the hands. Research is exploring new materials, like silicon rubber composites or nanomaterials, and even biomimetic designs inspired by human fingerprints to enhance sensitivity.
Any examples in current robots?
Yeah, companies like Sanctuary AI are integrating advanced tactile sensors into their Phoenix robots. They claim this helps enable capabilities like handling objects without relying solely on vision sort of blind picking or detecting if an object is starting to slip before it drops it.
Wow. Okay, so you have all these different sensors, cameras, LiDAR, force sensors, touch. How does the robot put it all together?
That's where sensor fusion comes in. It's the process of combining data from multiple sensor types to create a more complete, accurate, and robust understanding of the environment than any single sensor could provide alone.
So the whole is greater than the sum of its parts.
Exactly. It helps compensate for the limitations of individual sensors. Maybe the camera is blinded by sun glare, but the LiDAR still works, or the tactile sensor confirms contact when vision is occluded. Fusing that data gives a much better picture.
Okay, now let's talk about maybe the most complex part. The hands, the end effectors. Replicating human dexterity seems like a massive challenge.
It truly is a formidable engineering challenge. The human hand's range of motion, fine motor skill, and sensory feedback are incredibly sophisticated.
So how are roboticists tackling it?
Well, there are a few approaches. One is simply maximizing the degrees of freedom. Tile, giving the hand many controllable joints to try and mimic human articulation.
More joints means more flexibility.
In theory, yes. Tesla's latest Optimus hand reportedly has 22 diaph, which is quite a lot. Sanctuary AI's Phoenix hands have 20 dial.
How do they fit all the motors in the hand?
Sometimes they don't. Some designs use tendon-driven mechanisms. They place the motors further up in the arm, maybe in the forearm, and use cables or artificial tendons running down to the fingers to pull them closed or open them. This can keep the fingers themselves lighter and more compact.
Clever. Like our own anatomy.
Exactly. The actuation within the hand itself can be electric, often chosen for precision, or sometimes hydraulic for strength and speed, which is the approach Sanctuary AI has taken with their Phoenix hands.
And sensing in the hand is key too, right? The tactile stuff we mentioned.
Absolutely crucial. Integrating dense, sensitive tactile sensing into the fingertips and palm is vital for true dexterity, for feeling the shape and texture of what you're grasping, applying the right amount of force, and sensing if it's about to slip.
But there must be downsides to these complex hands.
Oh, definitely. There are significant trade-offs. Achieving high dexterity, robustness, and low cost simultaneously is incredibly difficult.
The trilemma again.
Yeah. Complex multi-dove hands are expensive to manufacture and maintain. Integrating and then processing the flood of data from all those tactile sensors is computationally complex. And simply controlling such a complex system in real time for fluid adaptive manipulation is a major AI challenge. Durability can also be an issue.
Right. Okay, so we have muscles, senses, hands. What keeps it all running? Power and compute. Sounds like another bottleneck area.
It really is. This area presents ongoing bottlenecks. The core issue is the high energy demand of dynamic robots versus the current state of battery technology. Actuators, sensors, and especially the powerful onboard computers all consume significant power.
So battery life is a big limitation. How long can these things actually run?
It varies a lot. Some specialized industrial robots might manage close to a full workday, maybe 20 hours, but current general-purpose humanoids often operate for much less. Aptronic's Apollo is quoted around 4 hours, Figure 02 perhaps around 10 hours on a charge.
That's not very long for work shift.
No. So this requires high-capacity, energy-dense batteries, highly efficient components throughout the robot, plus solutions like rapid charging capabilities or maybe even designing for easy battery swapping.
And just moving around and lifting things must use a lot of juice.
Absolutely. Power consumption requires careful balancing. You need high-performance strength, speed, payload capacity, but also energy efficiency. Dynamic movements like quick steps or lifting heavy objects require very high discharge rates from the battery, which puts a strain on it.
And then there's the brain itself, the onboard computer. Running all that complex AI must take a lot of power, too.
Definitely. Running complex AI models locally on the robot, what we call onboard computing or edge AI, demands powerful yet compact and energy-efficient hardware.
What kind of chips are they using?
We're seeing high-performance hardware being integrated. Figure 02 reportedly uses dual NVIDIA RTX GPUs for its onboard processing. Tesla's Optimus uses an adapted version of its full self-driving FSD computer. And companies like NVIDIA are actually developing specialized chips, like the Jetson Thor system on chip, specifically designed for humanoid AI, integrating powerful processors for multimodal AI tasks, along with safety-critical processors.
But putting powerful GPUs in a robot has limits, right? Size? Heat?
Big limits. The size, weight, and especially the power draw of these high-performance chips can constrain the complexity of the AI models that can run directly on the robot in real time. It impacts processing speed and how quickly the robot can react. And thermal management is also crucial. Packing all these dense electronics and powerful motors into a relatively compact, moving chassis generates a lot of heat that absolutely must be dissipated effectively to ensure reliability. Overheating can throttle performance or even cause failures.
And storage. They must generate tons of data.
Huge amounts. Don't forget data storage. Robots generate continuous streams of high-bandwidth sensor data video feeds, LiDAR scans, force readings. They need high capacity, high performance, and rugged storage solutions, typically NVMe SSDs, that can handle constant writes and endure the physical vibrations and movements without failing.
It really sounds like a deeply interconnected system. One weak link affects everything.
It absolutely is. Advances in hardware demand better power and compute solutions, while limitations in batteries or processing power can constrain the physical performance or the AI capabilities of the entire robot. Progress really requires simultaneous breakthroughs across all these different fronts.
Okay, we've explored the robot's physical structure, the body.
Yeah.
Now let's delve into its brain, the sophisticated AI models that make it intelligent and capable.
Right, and it's important to understand it's not usually a single monolithic AI brain, but rather a complex, layered stack of different AI models working together.
Layered. How does that work?
Think of it hierarchically. This modularity allows different parts of the AI to specialize in different tasks. At the very top, you have high-level reasoning and task planning.
The big picture thinking.
Exactly. This layer takes complex human commands, maybe given in natural language like, go fetch the blue screwdriver from the workbench, interpret the intent, understands the objects and locations involved, and breaks that command down into a sequence of high-level steps.
Like, navigate to workbench, scan for screwdriver, grasp screwdriver, return.
Something like that. Large language models, LLMs, and especially vision language models, VLMs, are becoming essential here for understanding the language, the visual context, and applying common sense. Figure AI talks about their Helix VLA having a System 2 that handles this kind of high-level cognitive processing.
Okay, so that's the top layer. What's underneath?
Beneath that is the perception and world modeling layer. This is where all that raw sensor data we talked about comes in camera feeds, depth maps, force readings, tactile data. This layer processes it all to build an internal representation or model of the environment.
Figuring out where objects are, mapping the space.
Right, identifying objects, tracking their locations, mapping the surroundings.
Yeah.
Using techniques like SLAM simultaneous localization and mapping, understanding the robot's own position and state within that environment. And crucially, this layer might also include predictive world models that try to understand how the environment behaves dynamically.
We'll come back to world models, I bet. What's next down the stack?
Then comes behavioral control and decision-making. Based on the current state perceived by the layer above and the high-level plan from the top layer, This layer selects the appropriate specific action or behavior to execute next,
So deciding how to grasp the screwdriver.
or deciding which pre-programmed skill to activate, like initiating a walking sequence or triggering a complex learned policy for a specific manipulation task, like inserting a peg into a hole.
Okay. And finally, the lowest level.
And at the bottom is motion planning and low-level control. This is the layer that translates the desired action or behavior from the layer above, move hand to coordinates XYZ, apply 5 newtons of force, into the precise, high-frequency motor commands that are actually sent to the individual actuators in the joints.
This handles the physics, the balance?
Yes, it handles the robot's kinematics, geometry of motion, and dynamics, forces involved, ensures smooth joint trajectories, implements feedback control loops to maintain stability, and track desired movements accurately. This layer needs to operate incredibly fast. Figure AI's Helix architecture refers to a fast system 1 policy dedicated to this kind of real-time control.
So these layers work together. Is there debate about the best way to structure this AI?
Oh, yes. There's a significant architectural debate in the fields right now between traditional modular systems versus end-to-end learning.
Okay, explain those. Modular first.
Traditional modular systems have clearly defined, often hand-engineered components for each layer, a separate perception module, a distinct planning module, a specific control module, etc.
Pros and cons.
The pro is that it can make debugging easier if the robot fails at grasping. You might isolate the problem to the grasping control module. But the con is that integrating all these separate modules so they work together seamlessly can be a huge challenge, very labor-intensive, and might lead to suboptimal overall performance because the interfaces are hand-designed.
Okay, and the alternative, end-to-end.
End-to-end.
Yep.
Learning, on the other hand, aims to train a single, large neural network that takes raw sensor input like camera images and directly outputs low-level actions, like motor commands.
One giant brain.
Sort of. And Figure AI's impressive coffee-making demo was described as being trained somewhat like this, where the robot seemed to learn the complex sequence directly from visual input by watching a human. Vision Language Action Models, or VLAs, like Google DeepMind's RT2, also push towards this philosophy, attempting to generate robot actions directly from visual and language input.
What's the appeal there and the downside?
The appeal is the potential for more holistic learning, maybe discovering novel or more efficient ways to perform tasks that a human engineer wouldn't have thought of. The challenge is that these models typically require absolutely massive amounts of training data, and debugging can be very difficult if it fails. It's hard to pinpoint why inside this giant black box network.
So where is the industry landing?
It seems many leading companies are pursuing hybrid approaches, trying to combine the strengths of both, using large foundation models like VLMs or LLMs for the high-level reasoning, language understanding, and semantic interpretation.
The smart part.
Right. But then using more specialized neural networks or even classical robotics control methods for the lower-level, real-time physical control where speed, precision, and safety are absolutely critical. Figure AI's System 1, System 2 architecture seems like this, and Sanctuary AI's Carbon platform also appears to be a blended approach. It's still an active area of research.
You mentioned vision language models, VLMs, a few times. Let's dive into those. The VLM bots, they seem really important.
Incredibly important. VLMs are a type of multimodal AI that can understand both visual input, images, video, and text language simultaneously. That's the key, understanding them together.
How do they function in a robot? Like a reasoning cortex?
That's a great analogy. They essentially act as the robot's reasoning cortex, especially for interaction. They are what allows you to give a robot a natural language command that refers to something in the visual scene, like your example earlier. Could you hand me the green mug next to the laptop?
How does it understand that?
The VLM processes the camera feed, identifies the objects, mug, laptop, understands their visual properties, green, understands the spatial relationship next to, and connects all of that semantic understanding to the intent of your command. Hand me.
So it links words to pixels, essentially.
In a sophisticated way, yes. They provide rich scene understanding, linking what the robot sees to broader semantic meaning and common sense knowledge, often learned from their vast pre-training data. They can help the robot understand properties of objects based on vision. This looks like glass, maybe it's fragile. Or figure out affordances, what actions are possible with an object. This has a handle, I can probably grasp it.
And they bridge the gap to the lower control layers.
Exactly. They translate that high-level semantic understanding into something the lower layers can execute. The VLM doesn't necessarily control the motors directly, but it might output a precise goal description like goal, grasp P, target, Object ID, green mug, location, XYZ, coordinates, constraints. Apply force gently.
Are many companies using these?
Yes, it's a major trend. We see examples like Figure AI's Helix VLA, specifically their System 2. NVIDIA is building their GR00T foundation model, which is described as a generalist VLM for humanoids, and Google DeepMind's research with models like RT2, which aims to directly output actions from vision and language.
What's the biggest benefit of using these VLMs?
A huge advantage, especially for VLMs pre-trained on vast internet-scale data, is their potential for zero-shot or few-shot generalization.
Meaning?
It means they can often understand and act on novel instructions or interact with objects they haven't been explicitly trained on for that specific task.
So you don't have to pre-program every single possible object or command.
Exactly.
Yeah.
Like telling the robot to find the checkered flag, even if it hasn't seen that exact flag in its specific robotics training data. Its pre-training on the internet gives it general knowledge of checkered patterns and flags, and the VLM can combine that abstract knowledge with its current visual input to identify the target.
That sounds much more flexible.
It dramatically reduces the programming burden and is a significant step towards truly general-purpose robots. It allows them to be instructed more like humans, using natural language and relying on their existing knowledge to handle novelty.
Okay, so VLMs handle the high-level reasoning and linking language to vision. You also mentioned world models. What role do they play? You called them the cerebellum.
Yeah, that's one analogy. World models are learned internal representations or simulations of the environment and, critically, how it behaves, its dynamics, its physics, cause and effect.
So the robot learns the rules of the world.
Kind of. It builds a learned simulator inside its own mind, you could say. Just as the human cerebellum helps with motor control, coordination, and predicting the sensory consequences of our movements, world models give the robot a powerful predictive capability.
Predicting the future.
In a limited sense, yes. They allow the robot to predict outcomes of potential actions before actually performing them. If I try to push this block here, how will that stack of other blocks shift? If I apply this much squeezing force to this egg, will it break?
How does it learn these physics?
Through interaction. Either extensive real-world experience, which is slow and potentially dangerous, or, more commonly, vast amounts of training within a high-fidelity physics-based simulator. From this interaction data, it learns implicit physics, things like gravity, friction, object permanence, basic material properties.
And this helps with planning.
Hugely. It enables a form of imagination and more efficient planning. The robot can use its internal world model to mentally simulate sequences of actions, evaluate the likely results, and choose the best plan while assessing risks. If I try to grasp this narrow object here, will I maintain my balance? Will picking up this item make the whole stack unstable?
Are these widely used yet?
They are an active area of research and development. NVIDIA is developing world foundation models, like Cosmos, designed to generate complex, realistic simulation scenarios and predict outcomes. DeepMind has published significant research in this area. Some approaches use digital twins, very accurate models of the robot and environment combined with physics engines to allow robots to imagine the consequences of actions in novel situations.
What's the impact if these world models become really good?
They're absolutely key to moving beyond purely reactive robots that just respond to immediate stimuli towards proactive, intelligent agents that possess foresight. They're essential for complex manipulation, navigating dynamic environments safely, and exhibiting less brittle, more common-sense behavior.
Okay, we've covered the AI stack, the reasoning VLMs, the predictive world models. How do these robots actually learn the skills in the first place? What are the main learning paradigms?
There are a few main approaches, often used in combination. A big one is imitation learning. Learning by observing or mimicking demonstrations, often from humans.
Learning by watching.
Essentially, yes. The simplest form is behavioral cloning, BC. This is supervised learning where the robot is trained on pairs of state action data recorded from an expert, usually a human. You show it, in this situation, state, do this action.
How do you get that data?
One common way is through teleoperation. A human remotely controls the robot using joysticks or VR controllers. It may be wearing sensors themselves, and the robot records its sensor readings, state, and the commands it received, action. Stanford's UMI system is an example of sophisticated teleoperation for collecting manipulation data.
Can they learn just from videos?
That's a newer exciting frontier. Learning from videos of humans performing tasks. Tesla claims to use this for Optimus, learning from first-person videos of factory workers. Figure AI's coffee demo was also based on observing a human, This requires sophisticated computer vision to understand the human's actions, infer the state of the world, and translate that into robot actions.
What are the challenges with imitation learning?
It's very data dependent. You need lots of high-quality demonstrations covering many situations. There's the correspondence problem. How do you map a human's actions with a human body onto a robot's body, which might be different? And there's a risk of compounding errors. If the robot encounters a state slightly different from its training data, it might make a small mistake leading to a bigger deviation and eventually fail completely because it's gone off distribution.
Okay, so imitation is one way. What else?
The other major paradigm is reinforcement learning, RL, learning through trial and error, guided by a reward signal.
Like training a dog with treats.
Kind of, yeah. The robot tries different actions in different situations, and it receives a positive reward for actions that lead towards its goal and maybe a negative reward or penalty for actions that are unhelpful or dangerous. Over many trials, it learns a policy, a way of behaving that maximizes its cumulative reward.
Where does RL usually happen in the real world?
Mostly in simulation. Because RL requires a lot of trial and error, potentially millions or billions of attempts, doing it in the real world is often too slow, expensive, and potentially dangerous. Simulation provides that safe, fast, parallelizable sandbox. Figure AI mentioned training walking gaits in simulation. Boston Dynamics heavily uses simulation for training Spot and Atlas. Techniques like domain randomization are crucial here to help the learned skills transfer to reality. Sim2Real.
Can you do RL in the real world at all?
It is possible, but it's much harder. It's very sample inefficient, takes too long, and safety is a major concern during the learning process. It's usually reserved for fine-tuning policies that were mostly learned in simulation, or for simpler tasks.
What kind of tasks is RL good for?
It's particularly powerful for tasks involving complex dynamics, like locomotion, walking, running, or intricate manipulation, where discovering an optimal strategy is difficult.
Advantages and disadvantages.
Advantages. RL can discover novel, sometimes superhuman solutions that weren't demonstrated. It can lead to policies that are very robust in dynamic or uncertain environments. Challenges. Designing good reward functions can be surprisingly difficult. It's often very sample inefficient, needs lots of data trials. The Sim2Real gap is always a concern, and ensuring safety during learning is critical.
Are imitation and reinforcement learning used together?
Yes, very often. Hybrid approaches are common. For instance, using imitation learning from human demonstrations to get an initial reasonably good policy, often called RLFD, reinforcement learning from demonstrations, and then using reinforcement learning to fine-tune and improve that policy further, making it more robust or optimal. This can significantly speed up the learning process compared to pure RL from scratch. Sanctuary AI mentioned training their hydraulic hands using RL in simulation, likely building on some form of initial guidance.
Okay, so imitation, RL, hybrids, all of this relies heavily on data, right?
Yeah.
Let's talk about the data pipeline. How does the data actually fuel this learning flywheel?
Absolutely crucial. The data pipeline is the whole process, how data is collected, processed, stored, and ultimately used for training the AI models. It's the fuel for the entire learning engine.
So first step, collection. Where does the data come from?
It can come from the real world. Human demonstrations via teleoperation or kinesthetic teaching, physically guiding the robot, observing humans, autonomous exploration by the robot itself, or crucially, data collected from a fleet of deployed robots like Tesla, leveraging its FSD data for Optimus potentially provides huge advantage, or comes from simulation. Procedurally generated scenarios, human-in-the-loop generation within the sim, or increasingly AI-generated synthetic data using world models, like NVIDIA's Cosmos generating training scenarios for their GR00T model.
Once you have the raw data, what happens next?
Processing and curation. Raw data is often messy. It needs annotation or labeling, which can be manual or automated, filtering and cleaning to select high-quality examples, normalization or formatting to make it suitable for the AI models, potentially data augmentation to increase diversity, like varying viewpoints, lighting, or using techniques like NVIDIA's Cosmos Transfer to adapt synthetic data, and rigorous quality checks.
Garbage in, garbage out, basically.
Precisely. Then comes storage and management. We're talking massive data sets, especially with video and sensor streams. You need robust, scalable storage solutions, often using high-performance formats and hardware like NVMe SSDs. Good data management practices like versioning and ensuring data integrity are vital.
And finally, training use.
Right. This curated processed data is then fed into the machine learning frameworks to train the various AI models, imitation learning policies, reinforcement learning value functions or policies, predictive world models, or fine-tuning the large vision language models for specific robotic tasks.
Can you give an example of a pipeline?
NVIDIA described a pipeline for their GR00T foundation model, starting with human teleoperation and simulation to generate initial demonstrations, then using AI to generate millions of synthetic trajectories based on those, augmenting that synthetic data using their Cosmos World model to improve realism and diversity, and finally using that massive data set for training the GR0T model.
It sounds like getting this pipeline right creates a competitive advantage, the data flywheel.
Exactly. It's a virtuous cycle. High-quality data leads to better AI models. Better models enable more capable robots. More capable robots can be deployed more widely or perform more complex tasks, allowing them to generate more and better real-world data. That improved data then feeds back into training even better models. Companies that can build and efficiently operate this data flywheel, collecting data, learning from it, deploying improvements, and collecting more data, gain a significant advantage. Collaborations like Apptronic partnering with Jabil for manufacturing can also help enable this by potentially getting robots deployed faster to start collecting data. It requires efficient collection methods, continuous learning infrastructure, skillfully blending real and synthetic data, and robust data management.
Okay, we've explored the concepts, the body, the brain, how they learn. Now let's talk about the players, applications, and the race to reality. Who is actually building these things?
This field is incredibly dynamic right now. There's been a surge of new companies, significant venture capital investment, all fueled by these recent breakthroughs in AI, particularly large models, and improvements in hardware.
It feels competitive.
Very. These companies are all navigating what's sometimes called the humanoid trilemma, the challenge of simultaneously achieving high dexterity, low cost, and broad AI generalization.
Hard to get all three at once.
Extremely hard. So the different approaches you see often reflect strategic trade-offs, maybe focusing initially on cost-effectiveness for simpler tasks, or prioritizing dexterity for complex manipulation, or leveraging massive data for generalization.
And then partnerships are key.
Absolutely crucial. It's increasingly an ecosystem play. You see hardware specialists teaming up with AI labs, robotics companies partnering directly with manufacturers like BMW or Mercedes for pilot deployments to get real-world testing and data, and tech giants like NVIDIA providing foundational AI models and computing platforms.
So let's look at where these robots are taking their first steps outside the lab. From lab to factory floor, early deployments. Where are we seeing them?
The initial focus is heavily on structured industrial environments. Places with relatively predictable layouts, repetitive tasks, often physically demanding or ergonomically challenging for humans.
So manufacturing is a big one, especially automotive.
Yes, automotive is a prime early adopter. We mentioned BMW piloting Figure AI's Figure O2 robot in their Spartanburg, South Carolina plant.
What are they doing there?
They're being tested for tasks like precisely inserting sheet metal panels into assembly jigs, things that require dexterity but are repetitive. It's part of BMW's iFactory initiative, looking at flexible automation to address labor shortages and automate tasks that traditional fixed robots struggle with. Figure AI's coffee-making demo also highlighted their focus on complex task learning using their dual-system Helix VLA.
Any other car companies?
Mercedes-Benz is also piloting Apptronic's Apollo robot in their facilities.
Doing what?
Tasks like delivering parts bins to the assembly line and potentially inspecting components. Apollo is designed with cost-effectiveness and integration into human workflows in mind. This pilot is Apollo's first major commercial deployment, a big step for them. They're targeting those repetitive, potentially hazardous or strenuous tasks.
And of course, Tesla with Optimus.
Right. Tesla has very ambitious plans, stating they aim to deploy thousands of Optimus robots within their own factories, possibly by the end of 2025, for things like material handling, logistics within the factory, and assembly tasks.
Using their own factories as a testing ground.
Exactly. It's a critical real-world testing ground and potentially a huge internal customer. Tesla's approach emphasizes a single end-to-end neural network, aiming for broad generalization, and they believe they have a massive advantage due to the vast amount of real-world visual data collected by their vehicle fleet for training their AI. They've shown demos like Optimus folding laundry or precisely threading a needle, showcasing fine motor control aspirations.
Beyond cars, what other manufacturing tasks?
We're seeing exploration for general manufacturing tasks like machine tending, loading parts into and unloading parts from CNC machines, or process assembly of smaller components, quality inspection using vision, sorting parts, and kitting, which is assembling packages of components needed for a specific downstream process.
Okay, manufacturing makes sense. What other sectors? Logistics and warehousing.
That's another major target sector. Warehouses are often labor-intensive, involve handling a huge variety of goods, and can be physically demanding.
Who's deploying there?
Agility Robotics Digit is one prominent example. It's being deployed by logistics companies like GXO Logistics.
What's Digit doing?
Tasks like moving plastic totes filled with items, picking them up from shelves or conveyors, and placing them onto other conveyors or carts. Digit is specifically designed with legs to navigate spaces built for humans, like stairs and uneven floors, and aims to integrate with existing warehouse management systems, WMS, and other logistics software. Figure AI has also reportedly had discussions with UPS about potential pilots for sorting small parcels.
What are the general advantages of humanoids in logistics?
The potential advantages are their ability to navigate human-centric spaces without major infrastructure changes. And crucially, the potential to handle a wide variety of item shapes, sizes, and weights, which is often a challenge for more specialized automation. Tasks could span receiving goods, putting them away, picking orders, packing, manifesting for shipping, and inventory management.
Any other early sectors? Retail, healthcare.
Retail is being explored, maybe initially for back-of-house tasks, but potentially front-of-house for customer interaction or shelf stocking. Aptronic has mentioned retail applications for Apollo. Healthcare is often listed as a long-term target by companies like Sanctuary AI, though current deployments are more focused on task-specific assistants like Moxie for hospitals, or social robots like Pepper, rather than general-purpose humanoids doing complex care tasks yet.
Why is manufacturing getting the first wave of deployments?
Several reasons. Manufacturing environments are generally more structured and controlled than, say, a home or a busy store. Companies in this sector are already accustomed to investing heavily in automation. There are often clear labor shortages or ergonomic challenges for specific, well-defined tasks. And critically, these initial factory deployments provide crucial real-world feedback to refine the technology, improve reliability, and hopefully drive down costs through manufacturing scale like the Aptronic-Abiel partnership aims to do. Manufacturing acts as an incubator for wider adoption.
Okay, so deployments are starting, primarily in factories and warehouses, but clearly we're not seeing them everywhere yet. Let's talk about the challenges, ethics, and the road ahead. What's holding back wider adoption?
Right. There's a lot of buzz, and people are talking about a potential ChatGPT moment for robotics.
Meaning?
An inflection point where the capabilities suddenly seem to leap forward exponentially, leading to rapid, widespread interest and adoption, much like ChatGPT did for conversational AI. NVIDIA's CEO Jensen Huang has even suggested this moment for general robotics might be just around the corner.
What would it take to reach that moment?
It likely requires a convergence of breakthroughs across multiple areas simultaneously. On the technology front, truly generalizable AI is key robust perception, common sense reasoning, the ability to learn quickly from limited data, maybe leveraging foundation models like GR00T. Improved dexterity for manipulating a wide range of objects reliably is still needed. Robust locomotion over diverse terrains and in cluttered spaces, and perhaps most critically for widespread use alongside people. Seamless, safe, and intuitive human-robot interaction, HRI. That means safety, understanding multimodal cues, predicting human intent, and achieving social acceptability.
And cost must be a factor.
Huge factor. Cost needs to come down significantly for mass adoption. While prototypes are very expensive, companies like Unitree are showing lower-cost platforms like their G1 at around $16,000. Tesla is aiming for perhaps $20,000, $30,000 for Optimus eventually. Some analysts project average prices could fall into the $50,000 range by 2050, but that's still way off. And it's not just the purchase price. The return on investment, ROI, needs to be clear for businesses, which means high reliability, low maintenance costs, and demonstrable efficiency gains.
Data is still a challenge too.
Yes, the data bottleneck remains. Getting large, diverse, high-quality data sets, especially from the real world, is difficult and expensive. So improving efficient generation and annotation methods, leveraging synthetic data from simulation and world models, better teleoperation interfaces like UMI, and making Sim2 real transfer more reliable are all vital for continuously feeding the AI learning process.
So it's probably not one single invention, but a convergence.
Exactly. It's likely the simultaneous maturation and convergence of these different factors, capable AI, dexterous hardware, affordable cost, and robust data pipelines that will make these robots truly useful, adaptable, and economically viable across many sectors, potentially triggering that rapid adoption phase.
Despite the progress, what are the big technical hurdles remaining right now?
I'd say generalization and robustness is still a major one. This is often called the long tail problem. How do you ensure the robot can handle the almost infinite variety of rare, unforeseen events, objects, and environmental conditions it might encounter in the real world? Current AI models, while impressive in labs or structured demos, can still be brittle when faced with true novelty. We need robustness against sensor noise, lighting variations, unexpected physical disturbances. Hardware limits also play a role: thermal resilience, storage robustness under constant movement.
And interacting with humans, HRI.
Human-robot interaction, HRI, remains incredibly challenging, especially for robots intended to work closely alongside people or eventually be in our homes. Safety is paramount. The robot must reliably perceive humans, predict their movements, and act in ways that avoid harm. This requires sophisticated perception, prediction, and motion planning, potentially incorporating compliant physical designs as well.
Beyond physical safety.
Intuitive communication is key. Humans communicate using much more than just words, tone of voice, facial expressions, body language, gestures. For robots to collaborate effectively, they need to understand and perhaps even generate these multimodal cues appropriately. Current LLMs are amazing at text, but integrating real-time understanding of nonverbal communication is still developing. And then there's the whole challenge of social acceptability and trust, designing robots that behave in ways humans find comfortable, predictable, and trustworthy. Managing the uncanny valley perception gap is part of this too. And the robot needs adaptive behavior, adjusting its actions based on the human state or feedback.
Any other major bottlenecks?
Dexterous manipulation, particularly with the hands and the AI control needed for fine motor skills, is still a grand challenge, especially for handling soft, deformable, or unknown objects. Power efficiency and battery life remain constraints. The cost of specialized components and scaling manufacturing is still high. Remember those planetary roller screws. And there are still fundamental AI gaps in areas like complex manipulation planning, common sense reasoning about physics in real time, and truly understanding nuanced human interaction.
Okay, those are the technical challenges. What about the bigger picture, the future of work? This must be reshaping economies.
It certainly has the potential to. It's important to think beyond just job displacement. There's also a huge opportunity for augmentation, where robots work with humans, taking over the dangerous, repetitive, or physically strenuous parts of a job, freeing up humans from more complex, cognitive, or creative tasks.
Like a collaborator.
Exactly. And the development, manufacturing, deployment, operation, and maintenance of these robots will undoubtedly create entirely new jobs, requiring new skills.
But displacement is a real risk for some jobs.
Yes. The risk is highest in roles that involve primarily predictable, physical labor. Think certain tasks in manufacturing assembly lines, logistics, and warehousing, like picking and packing standardized items, maybe some routine customer service interactions, or jobs in hazardous environments.
So we might see economic restructuring.
It seems likely. We could see significant productivity gains from robots operating 24/7 with potentially fewer errors and optimized workflows. This could impact wages, potentially putting downward pressure on wages for easily automatable jobs, while increasing demand and wages for high-skilled roles in robotics, AI, data analysis, and systems integration. This could widen the income gap if we're not careful.
So the demand for skills will shift.
Definitely. There will be a growing need for technical skills to design, build, manage, and repair these systems. But also, perhaps counterintuitively, soft skills or human skills become even more critical, things like critical thinking, creativity, complex problem-solving, collaboration, and especially skills related to human-robot interaction and managing these hybrid human-robot teams. This points to a massive need for workforce reskilling and retraining programs to help people adapt.
What about the ethical and societal implications beyond work?
They are profound and complex. We already touched on the workforce impact, but the scale and speed of that change is itself an ethical consideration. Then there are huge questions around liability and responsibility.
If a robot messes up, whose fault is it?
Exactly. It gets complicated fast. Is it the hardware manufacturer, the developer of the AI software, the company that owns and operates the robot, the human supervisor who gave the command? The lines blur, especially as these robots might have AI systems that learn and update continuously over time. It's not like a traditional product with fixed functionality. Various models are being proposed, like strict liability for manufacturers, shared responsibility frameworks, or even debated concepts like granting some form of electronic personhood for legal purposes, though that's highly controversial. Some places, like Japan, have specific laws regarding robot incidents.
What about bias in the AI?
Bias and fairness are critical ethical concerns. If the data used to train the robot's AI, especially perception or decision-making models, reflects existing societal biases, e.g. biases in images or text from the internet, or biased human demonstrations, the robot's behavior can inadvertently perpetuate or even amplify those biases.
Like discriminating in tasks.
Potentially, yes. Imagine a robot used in HR for initial candidate screening, or even in customer service interactions. If the underlying AI is biased, it could lead to discriminatory outcomes. Mitigation strategies include carefully curating diverse and representative training data, developing and applying algorithmic fairness techniques during AI development, actively auditing models for bias, and potentially using techniques for targeted data removal or debiasing.
And privacy. These things have cameras and microphones.
Privacy and surveillance are huge concerns. Robots, by their nature, are mobile sensor platforms, constantly collecting data about their environment, images, audio, potentially thermal data, location data, data about human activities nearby.
So surveillance in the workplace or even homes.
That's the risk. Pervasive surveillance in workplaces is a definite possibility, raising concerns about worker monitoring and autonomy. If they enter public spaces or homes, the privacy implications multiply. Key questions arise about data security. Who owns the vast amounts of data collected, how it can be stored, accessed, and used? There's often a privacy paradox where people express concern but still adopt technology that collects data.
How can we mitigate these privacy risks?
Mitigation involves adopting privacy by design principles during development, minimizing data collection to only what's necessary, anonymizing data where possible, ensuring secure data handling and storage. Transparency and control are vital, clear notices to people about what data is being collected and why, offering opt-out mechanisms where feasible. Regulation like GDPR in Europe or CCPA in California provides legal frameworks, and developing clear ethical guidelines for responsible data use is crucial.
This brings us to the regulatory landscape. How are governments approaching this?
It's evolving rapidly. The European Union has been quite proactive with its AI Act. It takes a risk-based approach, banning AI systems deemed to pose an unacceptable risk, and imposing stringent rules and conformity assessments on high-risk applications, which explicitly include many types of robots. It also mandates transparency requirements for generative AI models. The Act aims to balance safety and fundamental rights with fostering innovation, including provisions for regulatory sandboxes to test new technologies. It's expected to become fully applicable around mid-2026.
What about the U.S.?
The U.S. approach is currently more decentralized and often sector-specific. There have been executive orders on AI safety and trustworthiness, and various government agencies are issuing guidance. There are growing calls for a more cohesive national strategy, potentially a dedicated federal office, incentives for domestic development, and investment in training, partly driven by concerns about maintaining competitiveness, particularly with China. The focus tends to lean more towards promoting innovation and competition, perhaps with less top-down regulation initially compared to the EU. China sees AI and robotics as strategic priorities and is investing heavily to become a global leader. Regulation there is also developing, often intertwined with goals of technological advancement and maintaining state control and social stability.
Seems like international cooperation would be needed.
Absolutely. Given the global nature of technology development and supply chains and the potential cross-border impacts, there's a growing need for international cooperation on safety standards, ethical principles, data sharing protocols, and frameworks for liability.
Okay, so with all this context, the technology, the players, the challenges, the ethics, let's get to the big question. Expert timelines. When will we actually see these humanoid robots become commonplace?
Predicting the future is always hard, especially with technology that depends on multiple converging breakthroughs. But based on current progress, pilot deployments, and expert projections, we can sketch out a plausible timeline, though it's definitely subject to change.
Where first? Factories.
Factories are widely expected to see significant deployment first, likely becoming more common towards the late 2020s. As we discussed, pilots are happening now in major automotive plants like BMW and Mercedes-Benz. Tesla's goal of deploying thousands in its own factories by the end of 2025, if achieved, would be a major acceleration. Other manufacturers like BYD in China also have targets for thousands of robots in the 2025-2026 timeframe. Some industry analysts, like ID TechX, predict specific, well-defined manufacturing use cases becoming common around 2026-2027, with robots tackling more complex, varied tasks by the 2028-2033 period. A recent manufacturing survey indicated a large majority plan to increase automation investments by 2025.
Okay, factories first. What about other businesses, like logistics or retail?
Those sectors are likely to follow the initial wave in factories, seeing more significant adoption probably in the latter half of the 2020s and into the early 2030s. Logistics might see a major takeoff around 2026-2027, especially if the automotive deployments prove successful and bring costs down. We might see controlled public trials in places like shopping malls or hotels, perhaps handling specific tasks. starting around 2027, according to some analysts. By roughly 2029-2030, it's plausible that humanoids could be performing a wider range of tasks in these settings at a cost that becomes competitive with human labor for certain roles.
And the ultimate goal for many homes. When might we see them there?
Homes are generally considered the longest-term goal. The domestic environment is the most unstructured, unpredictable, and safety-critical setting.
Much harder than a factory floor.
Much harder. Major investment banks like Morgan Stanley have projected potentially 80 million humanoid robots in homes globally by 2050. But they caution that achieving this likely requires at least another decade of technological progress beyond industrial deployment, costs falling significantly, perhaps below $10,000 per unit, and crucially, achieving broad social acceptance and trust. Some analysts suggest limited consumer applications, maybe focused on companionship or simple assistance for the elderly, could emerge in the late 2020s, but becoming truly common might take well into the 2030s, contingent on that sub-$10K price point and proven safety and utility.
But some companies are aiming sooner for home trials.
Yes. Figure AI has mentioned plans for domestic alpha testing perhaps as early as 2025, and 1X Technologies is explicitly designing their NEO robot with home use as a target. So early experiments might happen sooner, but widespread household adoption is still likely a significant way off.
So what are the key milestones we should be watching for on this roadmap?
Keep an eye on continued cost reduction announcements of lower price points or large-scale manufacturing partnerships. Watch for demonstrable improvements in dexterity and manipulation, especially handling diverse or delicate objects. Progress in HRI robots interacting more naturally and safely with people in demos or pilots. Evidence of more robust sim-to-real transfer, where skills learned in simulation work reliably in the real world. Advances in AI generalization, particularly the ability to handle unexpected long-tail situations gracefully. Developments in regulatory clarity, especially harmonized safety standards. And finally, shifts in public perception and acceptance, which will be heavily influenced by safety incidents, successful deployments, and media narratives.
Okay, that's a great roadmap and watch list. So wrapping up this deep dive, what does all this mean? It feels like we're really on the verge of something significant.
I think so. It means we are truly at the cusp of a revelation, where artificial intelligence is transitioning from being primarily a digital tool, something on our screens, to becoming a physical presence integrated into the world around us.
And the intelligence itself is different, right?
Fundamentally different, yes. The intelligence of these embodied systems is grounded in that physical interaction through the continuous perception action loop. They learn by experiencing the world's physics firsthand, which gives them a type of understanding that purely digital AI, trained only on text and images, simply cannot have.
Building them is obviously incredibly complex.
It's a complex dance, absolutely. It requires simultaneous breakthroughs in both sophisticated hardware, from those high-precision actuators and complex sensors to the fiendishly difficult dexterity of hands, and overcoming the persistent bottlenecks of power and onboard compute, and increasingly advanced AI. Leveraging those large vision language models for high-level reasoning and common sense, potentially incorporating world models for intuitive understanding and prediction, and fueling it all with robust data pipelines and sophisticated learning methods like imitation and reinforcement learning.
And despite the hurdles, it's starting now.
Yes. While significant technical challenges and complex ethical questions undeniably remain, real-world deployments are starting now. Primarily in controlled environments like factories and logistics centers. These early deployments are providing crucial validation, invaluable data, and paving the way for refinement and eventual broader adoption across more sectors and maybe one day potentially our homes.
It's an exciting, challenging, and profoundly important transformation to watch unfold in real time.
Absolutely. So here's maybe an open question for you, the listener, to ponder as you think about everything we've discussed. Will this relentless pursuit of creating general-purpose humanoids fundamentally change our scientific understanding of what intelligence itself actually is? And thinking about public trust. Will people truly trust these walking, talking robots in our homes and workplaces before fully autonomous vehicles gain widespread acceptance and trust on our roads? Which hurdle comes first?
That's a great question to think about. We've really only just scratched the surface in this deep dive into embodied AI and humanoids. What aspects were you most curious about? What surprised you the most? Let us know what questions this raises for you.